Now let's talk about recrystallization for a little bit before we get into lab. In this experiment, you'll be given an unknown compound. It's a solid, and it's impure. It's got maybe about 10% of another solid impurity. This is very common. Reaction products very frequently contain byproducts or small amounts of impurities, sometimes large amounts of impurities. And there are multiple methods of purification. Recrystallization is a common method. So there are many types of recrystallization. The simplest is a single solvent recrystallization, where essentially what we make use of is we take advantage of differences in solubility between the desired compound and the impurity in a particular solvent. We also take advantage of the fact that solids have differing solubilities at low temperature compared to high temperature. So the way that this essentially works for a single solvent recrystallization, which is what we'll be doing in this lab, very straightforward and simple. We want a solid, or we want a solvent that the solid is minimally soluble in at low temperature. So when the temperature is low, the solubility is also low. But then as we increase the temperature, you see an exponential kind of increase in the solubility of the compound at higher or elevated temperature. And this is good for a recrystallization because what it means is that in a small temperature window, we can heat the compound in the solvent, cause everything to become soluble, but then when the temperature cools back down again, that compound, because of the large difference in solubility between the high temperature and low temperature, it will no longer remain soluble in solvent. It will crystallize out of the solution. And if we do this cooling process slowly, then it will have adequate time to come out of solution in an ordered fashion, providing a nice crystal lattice structure that replicates upon itself. And this tends to prevent any impurities from being trapped within those crystal structures. Additionally, if the solubility of the unknown, of the impurity is greater in that solvent than the solubility of the compound, then when it cools back down, that impurity will remain soluble in the solvent and may be removed simply by filtration. And that's essentially what's going to occur in this experiment. We need to identify a solvent where the unknown material is not soluble at room temperature, because if it's soluble at room temperature, then we won't be able to get it to come back out of solution in any kind of ordered way. We may not be able to get it to come back out of solution at all. So it needs to be insoluble at room temperature, but it needs to be fully soluble at elevated temperature so that we can get all of the material into solution, everything dissolved, and this will then allow, as we cool back down, to form those ordered crystals as the solubility decreases and the material begins to come out of solution in hopefully an ordered crystalline fashion. If we cool something too rapidly, if we have it hot and then we immediately dunk it in an ice bath, for example, what happens there is we'll have a rapid change in solubility between the high temperature and the low temperature, and we get what's known as precipitation. The material will crash out of solution, but it won't have time to form ordered structures, and so it will just kind of come out as an amorphous solid. That's known as precipitation. It's normally a dull color. It doesn't reflect light, and it tends to trap impurities within that structure because it hasn't had time to really slowly replicate upon itself as it does with crystallization. Crystals tend to have fine ordered structure. They tend to reflect light, and so that's one way you can tell the difference between a precipitate and a crystal is simply whether or not it's reflective, or basically is it shiny or not. So with a little bit of that background, we'll go to lab, talk a little bit more, and we'll get kind of right into the experiment. Here we are in lab. We've been given unknown number 9 here. It's a white solid, and we've been given it to recrystallize. Now, we know that unknown 9 is either salicylic acid, benzoic acid, or acetylsalicylic acid, which is actually aspirin. But we also know that it's been contaminated with maybe about 10% of an impurity. Urea is technically the impurity here. And so we don't know which of these it is, and if I take the melting point of it, the melting point is going to be significantly depressed, so I won't be able to assign positively which of the unknowns or which of the known compounds it corresponds to. So I need to do the recrystallization to purify the compound, and then I will be able to tell by melting point or mixed melting point measurement which of the known compounds this unknown 9 corresponds to. And when you start to do recrystallization, the first thing you have to identify is the proper solvent to do the recrystallization in. Now sometimes we'll have to do mixed solvents for certain recrystallizations. Here we should be able to get away with a single solvent recrystallization. And I've got several different solvents here, possible solvents. I've got methanol, we've got ethanol or ethyl alcohol, I've got ethyl acetate. And then I'm also going to use water as well as a fourth solvent, distilled water. And the way to measure the appropriate solubility is to take a small test tube, measure out a certain amount of compound, and then add a certain amount of solvent to it and shake it up and see what the solubility characteristics are like. Now, if it's soluble, if the compound is soluble at room temperature, then that solvent will not be good for recrystallization. We want a solvent that the compound is insoluble in at room temperature, but then becomes soluble in at elevated temperature. And so we don't want something that's very soluble at room temperature. We need something that only becomes soluble at higher temperatures to be able to do a good recrystallization, so that we have large differences in solubility at the different temperatures, at room temperature and elevated temperature. So what I'm going to do is I'm going to measure out approximately the same amount of solid into each of the 4 test tubes, and then I'll add approximately the same amount of solvent, one of each of these different solvents and then also water, to the test tube. In order to keep things relatively uniform, I've made a small mark on the test tube to indicate how much solid I should add, and then I've made another mark up above to indicate how much, where I should bring the level of the liquid. And then I've done that on all 4 so that we have approximately the same amount. So I'll begin with that, and then we'll test their solubilities and compare. Now I'll add approximately the same amount of solvent to each of them and vortex them in order to mix them well and see what the solubility characteristics are like. I'll do them kind of in the order that I have shown. I'll use water as the very first one, then methanol, ethanol, and ethyl acetate. All right, so at this point, let's compare them. So first, the water we see is entirely insoluble at all. In fact, it's brought material up along the walls just because it's so insoluble. So there's essentially no solubility in water at room temperature. Methanol is pretty much completely dissolved. So this would not be a good solvent to try the recrystallization in because we won't be able to get it to crystallize back out, since everything is fully dissolved, almost fully dissolved at room temperature. Ethanol is similar to methanol. There is undissolved material at the bottom, but not very much at all. This is not going to be an appropriate solvent for recrystallization for this compound. Then ethyl acetate, well, ethyl acetate has a bit more solid material at the bottom, but I'd say we've dissolved probably about half of the material. It's a little less soluble, but really still not very ideal for a recrystallization. You wouldn't get a lot of the material back. We probably dissolved about half here just at room temperature. That's not going to make for a good recovery later on. So of these four, what we would normally do now is that we would test the solubility of the various compounds in these solvents at elevated temperature. However, in the cases where compounds mostly dissolve at room temperature, then that's not necessary. You know that's not a good one to do. You do want to, if we had two that were pretty much completely insoluble at room temperature, then we would test them both at elevated temperature. We would heat a sand bath on a hot plate and test the solubility of those compounds at the elevated temperature in the two solvents and try to find the one where all of the material will dissolve at the elevated temperature. Here, since we only have one solvent that leaves the compound entirely undissolved at room temperature, we're just going to go ahead and try to do the recrystallization from water and hope that we can get everything soluble at elevated temperature. To perform the recrystallization itself, we will do this in what's known as a Craig tube. Here you can see it's kind of similar to a test tube, but it has kind of the slightly wider neck here. And we'll measure out our material into this. Now, in order to be able to calculate a percent recovery later, we need to know the initial mass. So I will first weigh the Craig tube empty. To do that, I don't want to place this on the balance. It won't stay very well since it's round. Instead, I will take a small beaker, tare the beaker, and then simply add my Craig tube onto the beaker to get the initial empty mass for the Craig tube. So now that I've got the empty mass for the Craig tube, I'm going to take the material that I want to recrystallize. Take unknown 9. And the exact amount that I need here is a little unclear. I don't need to take all of it. Certainly I couldn't do that. Here I'm just going to take 1 to 2 scoopfuls so that I have enough to be able to work with, and then I'll get the mass for it to figure out exactly how much I've got. So there I've got about that much. Let's figure out the mass for my initial material. So now we should be able to calculate the initial mass of my unknown. And I'm now all set to proceed to the recrystallization setup. So here we have the setup for the recrystallization. We'll have a hot plate with a sand bath in it. And I've got my Craig tube with my material. So what I will do at this point is I'm going to add a certain amount of solvent for the recrystallization here. I'll put a little bit of an excess. I want to add approximately up to maybe here or so on the tube of water. I don't have to worry too much since it doesn't dissolve at room temperature. There we go. got my water. I will then want to add a boiling stick to this just to prevent it from bumping. We talked about that a little bit briefly with the distillation lab. We don't want to get bumping here, and so this will hopefully help once the material starts boiling. Then I'll simply bury the Craig tube into the sand bath here on the hot plate. I could clamp it, but it seems to be fairly stable just as it is. And then I want to set the hot plate a little bit above the boiling point of water. Here I have a thermocouple that will tell the hot plate to raise the temperature of the thermocouple to the desired temperature. So here I'm going to adjust this down to about close to the boiling point of water. Now my material may dissolve before the water begins to boil, and hopefully that will be good. I simply want to sort of monitor it. I'll be able to sort of pull it out every once in a while, stir it with the boiling stick, and keep an eye and see, pay attention for when all of that material dissolves. Once all of the material is dissolved at the elevated temperature, then I will want to remove the Craig tube, let it cool. I can remove the boiling stick as well. Let that cool down to room temperature. That should induce crystallization of the desired material and hopefully leave the impurity behind, so still soluble in the solvent. And then from there, I'll be able to filter and collect my material. Let's start. So now that our material has crystallized, we need to be able to filter it to remove the solvent. Now this isn't very easy with a Craig tube where it looks like we have a lot of crystals stuck in there. It's not going to be very easy to get the material out under conventional filtering methods. But thankfully there is a useful centrifuge method for removing the solvent from a Craig tube. To do this, we take a plunger, shown here. We simply insert that into the top of the Craig tube. It's actually designed for that. And then we'll take a piece of copper wire, and I'm going to wrap it around the top of the plunger, just where there's a little bit more of a lip. I'm going to wrap it around that lip there a few times just to kind of hold it. I'm going to run that down to the little bit of a lip here for the Craig tube. So if I wrap it around the lip of the Craig tube, that simply now will hold everything together, and then I'm just going to wrap it a few more times to sort of get rid of the excess copper wire. Now, my two pieces are held together, and I can actually invert the system here without any changes. And what I'll do at this point is I'm going to take the tube, now I'll put it up right here for a moment, and I'll grab a centrifuge tube. And I'll take the centrifuge tube and I'll put the Craig tube upside down into the centrifuge tube like this. So now I've got the plunger roped to the Craig tube using copper wire and inside the centrifuge tube. This will now allow me to place this into the centrifuge right here. So I'll place that in. Now, anytime you use a centrifuge, you need to make sure that the centrifuge is balanced. And so directly opposite that, I'm going to put something that's approximately the same weight. Here's another centrifuge tube with a couple corks that's approximately the same weight as the Craig tube with its plunger. I'll set that directly opposite it, close the centrifuge, and then simply turn it on and let it run for a little while. And in this process, it will then, through just the kind of force that the centrifuge exerts on the sample, it will drive the solvent out of the little bit of space that's there, but the plunger will keep the solid material left behind. So we should be able to remove the solvent in this way. See that my centrifuge is not perfectly well balanced. That tube I put in to balance it must not be exactly the same weight. And so when I turn the rotation up on the centrifuge, it causes it to vibrate and move, which is unsafe. So we need to be careful about that. If we need to do more filterings this way, we can get a better balanced tube. But here, you'll see I have now removed essentially all of the solvent and left only crystalline material left in the tube. So this is perfect. We are now done. We can re-invert the Craig tube, remove the copper wire, carefully remove the plunger, and now I have isolated my solid material from the Craig tube. We will now place the sample in the oven to dry for a period of 10 to 15 minutes to remove any residual water in the crystals. So here we have our final isolated compound. It's cooled from the oven. We'll get a final mass for it. Now that we have our purified material, we will prep melting point samples for both the purified material and the original impure unknown. After taking those melting point measurements, we can then prepare a mixed melting point with the purified material and the known compound that we believe it to be. We can take the mixed melting point to confirm unequivocally the identity of the unknown compound. If that mixed melting point does not provide a positive confirmation, we can then do additional mixed melting point measurements to help identify the final, to provide the identity of the unknown compound.